ठीक है? Anything else that is not clear yet? Hello? So what is the challenge now? We said that there will be no leakage, but there is leakage happening. Huh? So what to do? We need to design something differently. So we say that so this VT loss thing we just now saw. Okay? You're able to see this? This VT loss is exactly what we saw just now. Any questions on the VT loss part?
So like for the static only, for example, you're saying that we are saying the VDD here as 2.5 volts. But as we, for example, scale to low technology nodes, this leakage would reduce because this VDD is decreasing. So on that also, if we are basically, so
you
this
tell me
leakage
you're
would be
reducing the
benefit for.
voltage. Okay, so you're reducing the voltage to,
Yes,
let us say, 1 volt.
yes, sir. VDD.
Threshold voltage would be 0.5.
Yes, sir. Yeah.
So at B you will have 0.5, which is VDD by 2. What would you make of that?
Yeah.
So in advanced technologies, it actually becomes worse.
Yeah.
Okay. So now what we say is, yeah, ye to chalega nahi. So let us put a level restorer. So after the inverter, we put a PMOS, a small PMOS, and we have a level restorer. And this, what does this level restorer do? It ensures that Vx goes to VDD. When V out is 0, Vx goes to 0 to VDD, and therefore there is no static current from the inverter. But what has happened? To make this gate, you already now have 4 transistors. Are you able to see this? So you already have 2 PMOSs now. You wanted to do away with the PMOSs altogether, but already you have 2 PMOSs now. Additionally, this additional transistor MR is like a load on the output, and you again have the same problem of ratio of the strength of MR versus MN. You want to drive something from A, but this MR is on. It will not let your Vx to go to 0. Are you able to see this? Suppose you want to drive X to 0. It was initially 1. If X was initially 1, then out was 0. Out was 0 means MR is fully on. Now you want to drive X to 1, X to 0. You want to sink that current through A. What happens? The amount of current you sink through a much more amount or some amount would be coming from MR. So this is again the same ratio problem that we were looking at in the earlier ratio logic paradigm. Are you able to see this? Any questions?
So the principle of layer restorer is basically the positive feedback kind of. If we
Yes, it's
observe.
kind of half latch. Yes.
Sir, what if we change sizes of MR and MN?
Yeah. So now you have to do the sizing, na? You have, see, in static CMOS, did you ever have to do sizing for your VOL or VOH purpose?
No.
No. You only did sizing for your delay purpose. Over here, we are saying we need to do sizing for functionality itself. Are you able to see this, Aditya?
Yes, sir. So now I will somehow decrease size of MR.
Yes. Now you want MR to be resistive.
Yes.
Huh? So MR has to be as resistive. Just like over there, PMOS had to be, the PMOS in the ratio logic had to be as small as possible so that you could take as close to 0 as possible. Over here, MR has to be as resistive as possible. It just is there to restore from Vx to VDD. Take from Vx to VDD. That is the only purpose. So keep it as small as possible. Typically, this restorer device would be the smallest PMOS that you could design in a technology. Smallest, and that too with large length. Okay.
Sir, having different lengths doesn't have any problem, right?
Having different,
Length.
yeah, if the length is minimum, then the current from MR will be high.
No, I am reducing the width also, right?
Yeah, you've already reduced the width. Yes, you are the minimum width. But if you want it to be still more resistive, what do? You increase the length.
Yeah.
So what I'm saying is size it appropriately. हो सकता है you may not need to increase the length, but हो सकता है you need to increase the length.
So, but we generally don't touch the length. Actually, I have not seen that people touching it.
You're not doing the CMOS course? You're not done the analog CMOS course?
Yes, sir.
So what
Like-
length are you using there?
Like here, I'm talking digital. Like most people are talking about width only.
So has anyone tied your hands that you don't have to touch length?
No, sir.
Then it is an assumption you're making. I'm telling you, increase the length.
But I think that opening the length would not only be like we are not going to deal with many things will change. I think so.
Yeah, let them. What all will change? Chalo, let's look at that. What all will change if you increase the length?
First of
All.
all, everything, the power also will change.
Which power?
I mean, dissipation, power dissipation also will get impacted. I think so.
Yeah, which power dissipation? Static or dynamic? We know everything now. We know all the different static power is gate leakage, drain leakage, junction leakage. We know all those components also. So tell me which one. If you increase the length, which power would increase?
Switching one, I think.
Which switching? In this particular circuit, which switching power would increase? The switching of out, because you've added an additional capacitor on out. Am I right?
Yeah. Yes. Sir. Yeah.
हाँ, तो लिखा भी हुआ है slide पे, है ना? So that will increase. So what has length got to do with it? Anyways, it was this MR you are putting. You increase the length by 10%, that capacitance increased by further 10%. So it's a minuscule change in overall power. But probably you are not now worried about ratio logic design. Your overall delay may reduce. That can happen.
Yes.
If you make MR more resistive, then A to X transition, A to X movement will be much faster. Because now MR is not really playing much role. It is only playing a role very slowly so that Vx does not remain at VDD minus VT level. Vx gets precharged to VDD. And that it can do at leisure. Output is already there. Are you able to see this? Devjit?
Sir, one thing just I wanted to ask that from X to the gate of MR, there would be always some inherent delay because there is an inverter. Now
Yes.
let's say my input was A1, then I suddenly switch to 0. Then for some time, won't we be observing a short between VDD and A?
यही तो बात कर रहे हैं इतनी देर से देवजीत. Why do you want MR to be small?
Oh.
This is exactly what we are talking about.
So then dynamic power would be increasing again.
Yeah, it would increase. It would take some extra time to, because MR ka current has to be sunk through A. That is not just dynamic power. All the current of MR in that period will have to be sunk through A.
Okay.
So if this MR is very large, then you will never be able to write 0 on X. यही तो बात कर रहे हैं.
Sir, the thing is actually in static CMOS, we never observed a short between input pin and supply pin. So
Yes. So see the
that's
challenge
what,
here. So this is a big challenge over here. Now your input pin, you cannot control it also. You see?
affected by supply, yes.
Yes. You see, this is such a big challenge. So
Yes.
later you will see, as we move forward, you will see that inputs, at least chip level inputs or block level inputs, can never come to pass transistor logic. Not allowed. Because some other circuit is driving, and over here you have put PTL, and this PTL logic, because of the virtue of it being PTL, starts to backdrive the inputs.
Yes,
The
sir.
system would
Slope
go,
will go bad, right?
everything will go haywire.
Yes, yes. Understood.
So no macro level inputs can ever be driven or can ever be taken to a PTL logic. Simply not allowed. You will see this in detail later. But so I'm happy that you've taken us to that point. But is this level restorer concept clear? Because we will use this in dynamic gates also.
So just here, so for example, all the techniques that we have studied, like the logical effort, we won't be able to apply here also.
No.
Is this right?
No. Logical effort is for static CMOS. These are techniques we are just trying to save area. Once you've done everything else, now you say, okay, let me recover area. So some places you say, okay, I will use this PTL. Some places you will say, I will use this DCVSL and all those things.
But here we are saving the area equivalent to only 2 transistors.
Yeah, वो भी नहीं हो रहा है.
वो भी नहीं हो रहा है
ना? So, but see, in this particular, you're just talking about one gate, then yes. But if you think of a mux, so see, this is the impact of restorer sizing. If the restorer is very large, then this is where your output is. But if the restorer is small enough, then it works. Okay. So this is okay. What you need to really look out for is that if you have two inverters, for example, driving this particular gate, there could be current paths that could form between them. Okay. So it's not easy. You have to be extremely careful when you use PTL. That is why I said these inputs cannot be coming from outside the macro. If you really have these two inverters, the input should be like coming here. Then whatever current it is, you will be able to characterize within your valid verification process itself. Okay. So what do? We had this VT drop and everything. To avoid VT drop, you instead of pass gates, you use transmission gates. Now what happens? Whether the input is 0 or 1, you will be able to transmit A to B. At one point of time, NMOS will be on. At another point of time, PMOS will be on. Are you able to see this? Instead of PTL, use transmission gate logic. Hello? So now you no longer need
This is
level
by
restorer.
adding one more transistor, right?
Yeah, but you no longer need the level restorer. Do you see that?
Yeah, it's
Huh? You no longer need the level restorer, and just to get, you do not even actually need to put the inverters there. If you do not have to drive a very large load, you just wanted to put the inverter just so that you have a clear 0 and 1 output. You no longer need that inverter also. So this is better.
so then why choose pass transistor logic?
I'm sorry?
Then why do we choose pass transistor logic? We can
Because
go
in
with
some places, pass transistor would work.
no, but transmission is better than
Yeah, but
Yeah,
at some places, in some places, you only need to transmit a 0. For example, in the bit lines of a memory, when you want to write into the memory, you only transmit a 0. That is the only transition that you are interested in when you want to write into the memory. So why then use a transmission gate? Why waste area? Area is gold. Are you able to see this?
So it depends on application which I will be.
Yes. So all these exotic styles, skewed gates, asymmetric gates, symmetric gates, all these exotic styles, this ratioed logic, PTL, all these exotic styles are to be used only on specific use cases. But when you have those specific use cases, you should have the library, you should have the mental space to say, okay, I have studied about this. Let me use this logic here. That is why we are discussing this in the class. Are you able to see this? Hello?
Yes, sir.
And ये ट्रांसमिशन में तो इसने तो सारी प्रॉब्लम सॉल्व कर दी पीटीएल वाली.
सारी नहीं करी, सारी नहीं करी, एक और प्रॉब्लम आएगी. So consider, for example, yes, काफी सारी कर दी. If you have a transmission gate based multiplexer, you can actually get a very good multiplexer out of it very quickly, no challenges. A transmission gate XOR is also very dense. Just look at it. Be careful. This is not ground. This is B bar. This is not VDD. This is B. Huh? These appear to be very nice designs. But realize that these A and B are now signals. So this B is not stable. B bar is not stable at 0. This B bar might also be rising or might just be falling. So the delays are not in your control at all. This looks to be a very dense design for a XOR gate, but try implementing it, try characterizing it, and you're in for a toss. Unless you have the world of time, you can't use this design.
So even if it is in the middle of some design, then I can control the signals. I can control the logic. Nothing can be controlled.
Yeah. ठीक है. So transmission gates के साथ ये देखो कि let us assume that there is a huge series of transmission gates that I have. What do I essentially have then? I have a large RC network, and my delays degrade humongously. So what do we need to do? We need to put buffers intermittently. Okay? We need to put these buffers intermittently. Otherwise, this is a very huge R equivalent that you will see. See, each R in itself is small. But because you have a multitude of these R's, it's like a stack of PMOSs or a stack of NMOSs. So you either need to size these transmission gates up significantly, or you just simply put buffers after, say, 5 stages or 10 stages or whatever is appropriate for you for that particular technology. Okay? So transmission gate ने बहुत सारी problem solve कर दी, but not everything. Are you with me?
So these
what's the
buffers would be
signal
CMOS
issue?
buffers, right?
Yes, this will be a regular CMOS buffer, 2 inverters.
Okay.
But you still save lots of CMOS areas, lots of logic area. Any questions here? यार आज मजा नहीं आ रहा है. Why are you guys not participating, not speaking? Nothing is happening. Friends.
Yes, sir.
What's happening? No response today. So if you have this kind of a transmission gate chain, then what do? You can actually calculate the delay. So if there is no buffer, then this will be the kind of delay, because the total number of resistance will be n into, you add all those resistances. But if you put in a buffer, then you will come to some optimal number. There is some delay of the buffer and then limited delay of the chain. So you arrive at an M optimal, total number of stages after which you should put a buffer. Okay. Are you able to see this?
I mean, like, I think that where exactly are we using these, like, kind of these esoteric, like, kind of circuits? Because we are
So
saving area.
transmission gate based circuits could be used at many places, because they will help you implement even complex logic with lesser number of transistors. Okay, it's like instead of PTL, you're using switches of transmission gates.
So,
Okay.
but then the early issue was that ना कि हमारे signals हैं अब सारे हर जगह पे. तो सर वो issue तो मुझे बहुत ही सारा लग रहा है कि that is a very very big issue, and I think.
Yeah, but that was for the XOR gate. No, don't get confused. That was only for the XOR gate. For other gates, it will not be like that. It can be, but not much. XOR gate was a challenge. XOR gate was designed like the XOR gate as designed like that appears to be very dense, but it's a pain. It's a pain to design it.
No, but sir, like for the other gates itself, for example, my suppose the B signal and the B bar signal, it would be coming from some other kind of logic. So then it would also be facing some kind of degradation, and the slew of that signal would change. And so how would I be able to characterize that? Okay, me, I will get this kind of my input signal at this transmission gate.
So again, I would say, रुको, उसके लिए अभी भूल जाओ. जो हम उसकी बात कर रहे थे, the thing that we were talking about in terms of what do you say, when we were talking about it in terms of so when we were अभी थोड़ी देर पहले when we were talking about it in terms of XOR gate, that is a different thing. All other gates you'll still be able to manage fairly well. Okay. So if we go to a buffered transmission gate chain, do you realize that there is a simple method to arrive at what is the optimal number of stages after which you want to put a buffer? Is this thing evident to you?
Yes, sir.
Great. So with that, we kind of come to a close of this PTL kind of logic design also. Okay. And now we start with what is called as dynamic logic. So what do you understand by dynamic logic? So I will just introduce